Yes. Okay, so thank you everyone for coming to the seminar. Today we're hearing from Robert Ott. So Robert did his PhD work at Heidelberg under the direction of Jürgen Burgess, and he was involved in a lot of kind of really early and kind of foundational work in the quantum simulation of lattice gauge theories. He also worked on the real-time formulation of quantum field theories. He graduated in 2022, and since then moved to the University of Innsbruck in Hannes Pichler's group. And during his postdoc, he's kind of run the full gambit of quantum simulation and quantum information, doing things from simulating quantum field theories to stuff with tensor networks and topological order. And more recently, he started working on error correction. And so that's what he's going to talk about today, is work doing error correction on fermionic quantum processes. So with that, Robert, please take it away.
Yeah, thank you. And yeah, let me say, I really appreciate the opportunity to tell you some of the work we've been doing in the last couple of months. And let me also use this opportunity right away to thank my collaborators, both in Innsbruck and abroad. So, of course, there's Peter and Hannes, who are very central in the development of all of these ideas, as well as Thorsten Sache, who's in Innsbruck, a postdoc as well. Also Daniel, who recently moved to Harvard, as well as Adam Kaufman, who's at GILA. And so, as Henry already said, here what I want to tell you about is a sort of concept that has been developed and put forward in the recent years, which is fermionic quantum computing and the idea of a fermionic quantum processor. And more specifically, the question that we ask is how we can sort of introduce the ideas of error correction in such a setup. And so I will tell you a bit about the challenges associated to that and sort of one of the solutions that we formulated recently in this archive article here. So with that, let me sort of jump in and tell you something about fermionic matter that you probably all know pretty well, namely that it's ubiquitous in physics, of course. And well, first of all, there's high energy physics, where it's sort of fundamentally fermionic matter is there in the standard model, in the Lagrangian, but also there are problems in quantum chemistry, for instance, where the interplay of electrons in the orbitals would sort of make up for much of the properties of molecules. Of course, in condensed matter, you encounter electrons and sort of fermionic statistics of effective excitations in materials. And more recently, I think there's also this question of quantum information and sort of the question what sort of changes for fermions with respect to qubits. And sort of central ingredients to fermions, I think, is the fermionic exchange statistics. So specifically in this picture here, and I'm sort of jumping ahead, thinking, you know, at fermionic atoms, so fermionic particles that you can maybe pick up with an optical light field, with an optical tweezer. And now suppose we had two of them, then of course if you interchange them and they're otherwise in the same internal state, they will be indistinguishable particles. But as opposed to bosons, they get this additional minus sign, which directly comes from the anti-commutating nature of the underlying operators. So this is sort of what changes with respect to bosons. And well, I'm going to tell you a bit about how this sort of affects these ideas of fermionic quantum processing with respect to the bosonic case. So by the way, please interrupt at any time if questions arise. So Yeah, I think that's sort of the background. So if we now think about quantum simulation, a typical strategy would be to sort of, you take your fermionic problem and then you find a mapping to a qubit system, and then you let it run on sort of available qubit hardware, a qubit quantum computer. And so typically this would require some overhead to do, yeah, because at the end of the day, what you do is you need to take into account this fermionic statistic, and you need to sort of introduce it by hand in terms of additional interactions between the qubits. Yeah, so this is something that has been done. So here's sort of a list of experiments that have been conducted in the recent years, notably built on architectures of like neutral atoms, trapped ions, superconducting qubits. And so this is a sort of list that's by no means complete, but sort of, illustrates that there's a relatively big amount of experiments which sort of have seen this effective fermionic dynamics in a bosonic hardware. But sort of what we're thinking about is, well, first of all, this overhead over here, and then sort of a natural way of circumventing such overheads by sort of making use of the unique possibilities that arise in platforms dealing with neutral atoms, because neutral atoms, they come in both bosonic forms as well as fermionic forms. And in that sense, they're maybe the only sort of platform where individual fermionic particles can be directly controlled in a quantum way with very high fidelity. So these platforms, therefore, sort of, a natural candidate to realize something like a fermionic quantum process. So on the hardware side, this is something that, similarly has been pursued for quite some time, for instance, in the context of optical lattices. So what you do there is you take, counter-propagating laser beams. They would form a standing light wave. This light wave would exhibit a force on the fermionic atoms and create this potential landscape that you see here. And so in practice, then, these atoms, they sit in these sites, they can tunnel through the lattice, they can hop around, and they can interact with other atoms. And this is an approach that, has been very successful and has shown a lot of very, very interesting results in experiments, notably in, famous groups in Munich, Harvard, MIT, and so on. And on the other hand, recently there is a lot of activity in sort of arranging atoms, as shown over here in optical tweezer arrays. So this is an old picture from one of these first experiments. And while this is showing here an array of atoms where the interactions happen sort of in a internal state of the atoms and simulate some spin physics between the atoms, you can of course apply the same principle to fermions. So you can trap individual fermionic atoms in these tweezers, and they have the great advantage that they can be moved, they can be reconfigured. So you're not limited to local interactions or sort of static Hamiltonians. So there are all sorts of things that you can play with these sort of systems. And this is an ongoing effort currently, really also on the fermionic side. So long story short, the idea is to, combine all these advances in the hardware that allows you to manipulate quantum matter in a very controlled fashion and build something like a fermionic quantum processors that sort of has been proposed and put forward in a couple of proposals recently. And here the idea is to really have hardwired fermionic statistics from the underlying fermionic atoms. So one idea that was sort of developed in Innsbruck, and that was is sort of what illustrates the way we think about this is essentially shown over here. So the idea is here you have these this array of tweezers, and now you can think of every tweezer essentially as a fermionic mode. This mode can be either empty, illustrated by the 0 here. It can be filled with an atom, illustrated by this 1. And so if you now have a number of atoms distributed among this set of modes, you essentially realize a fermionic Fock space. And well, from there you can manipulate the quantum states by all sorts of interactions. So one type of interaction is shown over here. And so what this realizes is essentially what we call a tunneling gate. So it realizes a unitary operator with a specific phase theta. You have here a quadratic Hamiltonian, if you wish, a tunneling of an atom between a side I and a side J. And they can be really distant. Yeah? You can rearrange the tweezers to sort of bring them close together, as shown here in the sketch, let them tunnel, and then sort of put them back, and therefore really realize this long distance tunneling without any additional overhead. And there's essentially different ways that you can realize this. Well, two of these ideas were sort of illustrated like this. One thing is the merge gate. So it's essentially here you see the two tweezers. They create this local potential for the atom. And you know, if you bring them together, the barrier would lower in between. The atom could tunnel over. You just leave this be for a while, and this time that you leave it essentially just determines the angle that you will get. And at the end of the day, you just separate them again, and you would get this delocalization of this fermionic atom between the two modes, which is essentially what you want for a tunneling operation. Similarly, you could play other tricks. For instance, you could have state-dependent tweezers. Yeah, for instance, you get a different tweezer at maybe a different wavelength of the laser. So you could change the internal state of the atom. It would now be trapped by the other tweezer. This tweezer, can transport this atom around, couple it to the second data tweezer over here, and then you can sort of play these tricks back and forth to essentially delocalize the position of all of these atoms, and therefore manipulate this Fock state in all the different ways. Additionally, you can also, yeah. Sorry, was there a question?
No, I don't think there was a question.
Okay. So a second thing that you can do is what you could call an interaction gate. So basically, again, you could bring two tweezers together. You can bring these two atoms to an interacting state, let them interact for a while, and sort of reverse the process. And you would realize a gate, something like this, which would be a relative phase depending on the occupation of the two atoms. And so actually this sort of gate is not really depending on the fermionic nature. There's no real exchange phase that plays into that. So it can be essentially realized in a similar way, in the same way that, well, these Rydberg interaction gates, for instance, work also in the qubit case. And now you can essentially think of these gates as building blocks, which allows you to sort of systematically build up more difficult unitary operations. Sorry. For instance, there is a density-dependent tunneling gate that you can realize. So you can tunnel between modes I and K, depending on the occupation of a third mode over here. And you can decompose this into these elementary gates with a certain combination of angles. And similarly, you can, for instance, have here this, sorry. Try, sorry. You can have this pair tunneling process over here. between modes I, J, K, and L. So this will be a non-Gaussian operation that you can decompose in this way. So with this, you can essentially also realize a universal gate set. There's a you're at specific angles, and there's a caveat. So this caveat is essentially, sorry, I don't know what's happening, the voice. So since you have a fixed number of atoms in this tweezer array, it's of course forbidden to do number changing processes. And this turns out to be a major restriction for the gates that you can play. Yeah. So because you cannot create atoms from thin air or remove them in a simple way, in a unitary way, it's of course forbidden to create such an operation in a straightforward way. So it turns out, however, that you can still, at a certain angles, you can realize a universal gate set with such that within this particle number sector, you can essentially realize any unitary that you want. So this has full universal power within this particle number sector, which will be then essentially enough to simulate any physical problem that also operates in a fixed particle number sector. Yeah, so in this sense, you can get a universal fermionic quantum processor with these sort of operations. Okay. So, of course, there's a lot of experimental challenges associated to that. Of course, all of these operations are difficult to implement in practice, and they would all come with associated errors and so on. So typically, if you have an atom in a tweezer, you move it around. If there's a stray field that you didn't take into account, you would get an extra phase and therefore get dephasing in the end. And essentially, you have these sort of problems at every step of the way. So you need to make sure that you have a good state preparation. You need to take into account scattering that you have with the tweezer. Rydberg gates might not be perfect. Moving of the atoms is, as I said, difficult and takes a lot of time. So there's a lot of sort of problems and sources of errors, and the corresponding solutions would probably involve some sort of error mitigation. Another idea is to use an optical lattice as a register. So typically, optical lattice can be held more stable than tweezers, which can sort of have mode-to-mode fluctuations. So there are a lot of sort of hardware optimizations that you can do. At the end of the day, you would nevertheless probably need something like quantum error correction to really make these sort of computations scalable. So in that sense, the challenge that we set out to do is the question of how to implement quantum error correction for such fermionic quantum processes. And as it turns out, here this atom number super selection is really a difficult task. Yeah, so if you think about standard error correction, one thing that you do is you take your qubit register and you can sort of divide everything into individual code blocks, and then you can think about error correction on the level of these code blocks. But the difficult thing here is that actually, because it's a fermionic Fock space, of course, the Hilbert space structure is more complicated. It's not a simple tensor space. And as it turns out, this complicates the entire story a lot. And so in the following, I want to dig into a few of these details. But so before I do that, I would still sort of briefly recap quantum error correction. So I'm not sure how sort of familiar everybody is. So please interrupt me if something's unclear. I would nevertheless briefly go through an example. And let me first say that, well, quantum error correction at the end of the day, it's a story about how we can protect quantum states by, well, not sort of directly encoding them into the state of an individual microscopic object, but rather you take a selection of these objects, you interact, let them be entangled in a specific way, such that you can encode and sort of hide your information in a suitable subspace of that, if you wish, many or more particle system. And well, if you just think about the basic approach, sort of what I was talking about so far, you have sort of one particle, you have a certain internal state, and you encode the quantum information of this system into its internal state, maybe an electron as a spin being up or down. Then essentially here the quantum information sits in these coefficients alpha and beta, which will tell you sort of the relative occupation as well as the phase between the two states. So you now might have something like a dephasing operation, which might apply something like a Z operator onto the state, an operator that you maybe didn't want to apply in the first place. And also you don't know that it was applied. So at the end of the day, it sort of erroneously would flip the sign of this beta and therefore directly corrupt your quantum information. So instead, what you could do is you could encode your state. And perhaps the simplest example to look at is something like a repetition code. And so here, what I mean by this is you take three of these atoms, and you let them point into the x direction of the Bloch sphere. So each of them would be sort of a superposition 0 plus 1. And you take the corresponding 3 atoms pointing in the minus direction. So if you look at that state and you now have a dephasing error on one of the modes, for instance, on like the third atom, what would happen is actually you would flip the direction of this atom from plus to minus over here and from minus to plus over here. And you right away see that something different has happened. Yeah, while the individual states that you used to encode now have changed, the beta and the alpha are still preserved and remain untouched. So now there's actually a measurement that you can do. And so what you do is you measure syndromes. And here you take a product of 2 Pauli operators. Well, one operator, which is the product of Pauli X at position 1 and 2. And you take the product at position 2 and 3. These 2 operators commute, so you can simultaneously measure them and get a well-defined measurement outcome. So let's look at the state that we encoded and that has not been affected with an error. So it turns out that it's an eigenstate to both of these operators with the eigenvalue 1. So you can measure these operators, you get back the measurement result 1, and you don't do anything, and you can pass along the correct state, and everything is fine. So suppose this error happened over here. You again do the same measurement, but actually since this operates at Z3 anti-commutes with X3, and therefore the second operator over here, you would flip the measurement result to -1. You would get a state which is the erroneous state. However, from the measurement outcome, you can uniquely identify which error has happened. You apply a corresponding Z3 operator to correct the state in like a post-processing step, and you can again pass along the correct state. So this sort of shows you that, you know, if you suitably encode, do the correct time of measurement, you either project into a good subspace or you project into a bad subspace. But if you project into the bad subspace, you also know in which subspace you projected, and you can reverse the operation. So more generally, there's a set of error correction conditions which sort of tells you if your logical state, here denoted I or J, are a suitable code corresponding to the errors E that you label with an index. And so they essentially tell you that this condition has to be fulfilled for some Hermitian matrix C. And essentially, it also tells you it needs to be orthogonal in the logical basis. And what tells you, loosely speaking over here, is something like this, that if you have an error, which is, for instance, here a Z acting on any of the atoms, you would expect that, in both logical states, the expectation value of this operator is the same. Meaning from the measurement of the Z, sort of from the knowledge of which error has happened, you should not be able to infer which logical state you had. So you cannot sort of collapse the quantum information. So in this sort of illustrates what the problem is going to be now with the number super selection. So if you sort of blindly copy this for the fermionic story, then this would just tell me, okay, I should bring everything in such a repetition code, encode everything in the plus minus basis. But actually here you encounter an issue, because none of the states that I showed you before were in a fixed sort of number sector. And so it actually turns out to hold more generally. It's actually sort of impossible to define a code block in this way, which sort of uniquely protects a single fermionic mode from dephasing errors in this way. Yeah, and the underlying reason is the super selection rule that you cannot create or annihilate atoms sort of fundamentally in these machines. So the sort of solution that we propose in this case is well, something that we call a fermionic reference construction. And so while we can sort of pictorially think of it in this way, we can think of a system, which is essentially the data modes. So you can think of this as the 3 data modes, which we combine to form such a repetition code as shown earlier. So this would sort of show you 3 logical modes. But additionally, we let it interact with a global reference that is something that doesn't do any computation by itself. So it doesn't need the full rearrangement capabilities of a tweezer array. So it can, for instance, be stored in a much more stable optical lattice as shown over here. So now what we're going to do is we're going to tailor the reference states and the interactions between system and reference in such a way that we can essentially let the system allow to take atoms from the reference and therefore create effective number changing processes in the system, where the reference just stays in the back and it essentially is just a reservoir for all of these fermionic atoms. So for a specific example, you could think about sort of the first mode over here, and you may start here with empty tweezers. And let me denote this entire state here as 0, 0, 0, indicating that there's no fermion in the tweezer modes. However, we start with a filled reference. So if I now want to create a fermionic atom in the first tweezer mode, what I can do is I can, in a well-controlled way, pick up the first fermion that I get in this reference state and move it over to the tweezer. So if I do this, I get that relation between these 2 states. And I have sort of an operational definition of what CDagger is supposed to do. Namely, it's supposed to create a fermion in this tweezer mode, and it's supposed to annihilate an atom from the reference state. It turns out if you sort of use the right operational definition for this R, then the C would inherit fermionic anti-commutation relations from the underlying commutation relations of the S. And in such a way, I will show you this in a bit more detail on the next slide. You can create quantum superpositions in this case. So you can see the atom number is the same in each of these basis states over here. But, well, the order here is sort of giving you an information on the occupation states within the tweezers. However, this reference operation is constructed such that you would sort of always pick out the leftmost of the reference atoms. So in this way, actually, the reference state is uniquely determined by the occupation number, so the number of remaining atoms therein only. and therefore this R doesn't have a local structure, and therefore the local structure would only be determined by the tweezer modes over here, which is then what sort of allows you to carry over the fermionic statistics to these effective particles that you define in this way. So
Robert,
yes.
Can you control which trap you move the atom, you move the reference atom to?
Yeah, so I mean, here comes in the rearrangement capabilities of the tweezer. So, well, in a simplified way, you can essentially, move the tweezer onto the lattice side and pick up the atom from there. I mean, literally like with a tweezer, and sort of move it back. And so you have, in principle, full local control over all of these processes.
I see. Okay, thank you.
I also have a quick question. So how would you comment in terms of scalability of this? Because it seems like every time I have more system qubits of system fermions, I'll need a bigger and bigger reservoir in order to make sure that happens. And in order to create those superpositions, I have now spatially a wider and delocalized system, and it will decrease the decoherence time significantly. Am I getting that wrong?
No, that's right. So I will show this in a more detailed way in the next slide. But actually, it turns out that the system reference operation is extensive, meaning sort of the more logical modes you have, the more accents to particles you need. So you need more and more atoms in the reference. And it's difficult to say a priori where the atoms are going to sit. So you always pick them up from the left side to sort of have a well-defined ordering in which the atoms go out and go in. But actually, you will have a large superposition of different occupations over here, as sort of indicated by the different shading of these atoms. So a priori, if I tell you that I want to pick up an atom to put it back in here, the tweezer need to sort of talk to each lattice side once and ask it, hey, do you have an atom that you can give me? And it would sort of find the last one and pick it up. But in that sense, it's an extensive operation. And we're currently looking into the question to what extent this is a fundamental limit for such an approach.
Thank you.
So, well, maybe digging right into this question in a bit more detail. What we want to realize is essentially rotations of this sort. Yeah? Something that in a qubit language would be an X operation, which changes the 0 to 1 and vice versa. So if you map this to fermions, this would correspond to something like a sum of a creation and an annihilation of the fermion. And actually, if I replace this now by this operator that I introduced, it would look like this. And essentially what the R does is, as I said, it would pick up the last fermion in this occupation. Yeah, so you have this lattice, they're occupied all from the right with single occupation. And at some point, there's the domain wall, and from there on, it's empty. So we plug in here an operator which achieves the tunneling, but additionally checks the occupation state to find out which fermion it needs to tunnel out. And it turns out it can be decomposed in such a way. And essentially, as a circuit, you can draw it like this. So you have an operation like here, and this operation sort of would apply relative phases. And these relative phases essentially find out whether or not this mode is the domain wall, sort of the last fermion that you want to take. So if these ones give you, thumbs up, then this operation would tunnel the fermion out, or vice versa, tunnel the other fermion in. And in this way, you have a density controlled tunneling operation, which does the exchange. But in fact, you have to go through the entire reference system to figure out. It might be that only this mode over here is occupied. because all the other reference particles are already in the system. So if you take out another one, you would ask all the way, figure out that all of these are empty, and then with this one, sort of pick up the last one. So in that sense, it's exactly this question. It's an operation that scales linearly in the number of atoms and therefore linearly in the number of logical modes that you want to encode in the system. Okay, so with this, the idea is to, well, then realize code states. So locally, you can think of code states in such a way, and actually it's maybe a bit in disguise, but it's a repetition code similar to the one that I've been showing you earlier. So it's 3 modes, and a vast superposition of the different states. And here the defining feature is the fermion parity. So you have something that you call a logical zero if actually the fermionic parity is even here, meaning there's an odd number of fermions inside of these 3 modes. And reversely, if you have an odd number of fermions, you would call this a logical fermion. Yeah, and this makes sure that sort of you inherit the parity from the hardware level, such that if you take 2 of these ones, logical ones, and you exchange them, you would get the correct exchange phase. Similarly, you can define 2 stabilizers. They are the fermionic analog of this product of X operations that we were measuring earlier. And importantly, as I said earlier as well, these operators, they commute, so you can simultaneously measure them. And they also commute with this big Z operator over here, meaning that this operator, as defined in this way, would stay in the logical subspace, and therefore it's the corresponding annihilation operator, which will bring you from this logical 1 to this logical 0. And of course, there's a corresponding creation operator as well. So, and with this, the idea is then to, realize a sort of a set of operations in this way. You would have a dephasing operation by whatever influence of the environment you have as a consequence of imperfect implementation of your operations. You could then bring in this reference construction and exchange particles to measure these 2 operators over here. And depending on the measurement result, you could again apply a phase by changing the local light field, for instance, to counteract this error and get back the original state. So in a bit more detail, we can draw a circuit for that. So again, we have this construction here, which effectively applies this X operator. And if we do this here with mode 1 and mode 2 in combination with here, for instance, a qubit ancilla, then actually this sort of circuit would make sure that the value of this stabilizer S12 is engraved into the measurement result of this ancilla qubit over here. And then you can do the same thing for the second stabilizer, and you can measure the 2 ancillas over here. So again, on a hardware level, you do this by bringing in the reference construction and interchange the particles, so between reference and system. And from this measurement over here, there's a set of 4 combinations that you can get. So either both of them are 1, then everything's fine. But actually, you have 3 ways of not getting both 1s, and they would uniquely be associated with the corresponding correction. So if 2 and 3 is flipped, as in the example before, I would apply an e to the I pi n 3, which is the phase flip on the last mode to correct the error, and similarly for the other combinations as well. And with this, let me come towards the end. We have well compiled and simulated an example circuit. And so basically what we looked at is the exchange phase. So suppose you have 3 sets of logical modes. So well, 3 modes that can be occupied with a logical fermion here and a logical fermion here, while we keep a logical vacuum down here. And we call the state psi1, 2. And essentially what you can now do is you can very easily just, exchange the entire set of tweezers corresponding to the respective modes. And by this, you can essentially reorder the logical modes and bring this to the second one over here and exchange this to this one and get a state psi2, 1. And by measuring a relative phase, by doing sort of an interferometric experiment involving this process, we can find out if the underlying particle was a fermion or a boson in this way. So you can think of a circuit like this. So you initialize an ancilla qubit, apply a Hadamard, it's a 0 + 1, and now controlled on the state, you can exchange the logic fermions over here. And actually, it turns out if you measure in a suitable basis, you will get +1 if it's a boson, and you will get -1 if it's a fermion. And what we then did is we applied a set of errors. So essentially, we apply a dephasing channel after every set of operation, and we apply a subsequent layer of correction. And essentially, what happens is can be seen over here. So this is the exchange phase +1. So if it's a fermion, this all should go to 0. And if you just apply the circuit with a certain error strength, which is essentially the probability for each mode to see a phase error in these layers, you see how if you reduce the error strength, you get a better and better result. And well, you see that essentially with error correction, you can push the error strength from p to p². So therefore, you reduce every system, like you remove every single error that happens in a code block, and you only fail in the cases where 2 errors happen at the same time, which is a case that you can in principle cure for by scaling the code distance. So if you apply more and more complex codes, you can essentially push this further down to, p cubed, p4, and so on. So with this, let me summarize and well, say that I hope I convinced you that this reference construction allows you to overcome this particle number constraint in this fashion that can be implemented with hardware that is developed at this moment. We can apply this construction to quantum error correction, and we can now think about more general concept from the quantum error correction framework and see how it can perhaps be imported in such a construction. And I think one of the big questions is, while I showed you the simple example for an easy case of correcting a phase error there are more complicated and bigger questions on a path towards a full fault-tolerant fermionic quantum processor. And here we're sort of just at the beginning of figuring out how this can be extended. And also I showed you one of these reference constructions. In principle, there's a multitude of things you could do. And I think it would be interesting to also think about different hardware implementations of actually doing this. And well, more generally, I wanted to highlight these final 2 points, which essentially, well, also to stress that I think it's also maybe a nice motivation for new theoretical developments, thinking in the direction of fermionic quantum algorithms, and also really figuring out where advantages can be gained from directly having this fermionic statistics at the hardware level. And also going to other quantum information applications beyond simulating fermionic physical models. Okay, with this, let me thank you and again, thank my collaborators. And yeah, happy to answer questions if there are any.
And so thank you, Robert, for the very nice and inspiring talk. Does anyone have any questions for Robert?
But I have a naive one. Like, what is the physics behind this power law improvement? Like P goes to P squared.
So essentially, wait, something. I think you can see it from this example over here. So essentially, well, I showed this example where a single Z3 error hits the state here. And essentially I tell you, okay, when I measure these operators and these operators, so I notice, okay, there's a Z3 happening, and I apply a Z3 and I get back the same state. But essentially this example relied on, well, sort of the choice, if you wish, of just applying a single Z operator here. So what I say here is if there's a single error happening, then it's enough to encode it with these 3 atoms and then correct it. But actually it turns out that if you apply 2 errors, so if I had applied Z3 times Z2, for instance, then I actually would have made a logical mistake in the end. And you can see it directly. So don't apply Z3, instead apply Z1 times Z2. Actually, the measurement outcome here will be the same, yeah, because Z1 times Z2 would commute with this operator, so it wouldn't change this one. And Z1 times Z2 still anti-commutes with this operator. Yet again, I apply a Z3 because from this measurement result, I assume the Z3 happens because it's a more probable result in the case of dilute errors. So I would have, in fact, sort of applied a logical Z operator as a correcting procedure and therefore flip the beta. So in that sense, if you do this error correction, you remove all errors at order P, but you keep the ones at P squared.
Yes. Yeah. Very nice. I got it. Thank you.
Yeah.
So I have some utility-based questions. So if you want to try your protocol on the devices, which I believe is in your Outlook bar. So what numbers are we talking about with the current or projected device parameters? How many reference qubits of reference fermions do you need? How many logicals can you construct, and how many operation or what circuit depth can you do? What are the rough estimates so that I can think what problems can be suitable for this?
Okay, to be very honest, we haven't really made a quantitative estimate.
Okay.
So one thing that we did was this example circuit. And so I think it's one of the simplest circuits that you can do to, well, probe this logical exchange phase, which highlights this fermionic statistics directly in an experiment. So, but maybe you can get some estimate for the numbers, yeah, because here you see this is essentially 6 layers of operations. And so this error strength is the probability of each individual mode at every of these 2 layers failing. And what I don't show here is the reference, and the reference is has well, for each logical mode you need 2 extra atoms to exchange with the system. So in this case, the reference would have 6 atoms. So in total, you have you initialize 2 logical fermions, this is 2 extra fermions. So in total, you have 8 fermions in 9 modes, plus 6 reference modes and an ancilla, and you have I don't know, order 10 operations. And if your every gate fails with a probability of 10%, you end up somewhere here.
All right.
But very rough estimate.
Okay.
So I have a couple questions. So something that I didn't really understand is when you were talking about how this reference operation is extensive. So you kind of have to search the whole reference register when you want to exchange fermionic particles. And because I thought that you take particles from the reference in kind of a very ordered way. And so why can't you just keep track of kind of where that, I think you called it a domain wall is, and just go immediately there when you want to exchange particles instead of like searching the whole thing until you hit where it is?
I think we're still digging into this question, whether it can be done more efficiently or whether this is fundamentally limited by that. But pictorially speaking, well, where did I illustrate this? I mean, you see it a bit here. Suppose you have a collection of zeros and 1, then for each mode, you have a change in atom number, which is 2. So suppose you take 3 zeros, then the reference is in a coherent superposition. It's entangled with the system modes. But in the state, the reference can have occupations from 0 to 6. And it needs to be a coherent superposition of those. That means in each of these states, the domain wall is at a different place. But because it needs to be coherent, you cannot classically have the information of where the last fermion sits. However, the position of your tweezer is a very classical control. So you cannot tell your tweezer where to go to pick up the fermions in this classical fashion. And therefore, what we say is, okay, go with the tweezer through every of these modes and then do a quantum operation which implements if something is occupied in such and such ways, do the tunneling or don't do it.
Okay, so it's really like the superposition and kind of keeping that coherent. Okay.
And this superposition is essentially, at the end of the day, the same coherent superposition that you need for quantum error correction. So because in the code block, it needs to be a coherent superposition, it therefore also needs to be the same coherence in the reference. If I may use these words in this way.
Okay. My second question is, I know in these neutral atom platforms, so the gates usually can be done quite quickly, but kind of one of the limiting things is like the readout and measurement, which happens quite slowly. Do you see that as being kind of the primary hardware obstruction to doing it? You're right, because if you're doing like multiple rounds of error correction and you're constantly having to like measure things and then go back in and correct, do you see that as being kind of like the big bottleneck for implementing this?
Certainly, this is a big restriction. So I think atom movement typically is slow. So moving the tweezer without exciting the atoms too much takes a long time, and measurement usually also takes a long time. I think there are a couple of ideas around how to speed up this process, but I think at the moment these are the limiting factors. And in this sense, here we have the same limiting factors as in the current platforms pursued, for instance, in Harvard.
Okay, thank you. Does anyone else in the audience or online have any questions?
Okay, quick one.
Sora?
Yeah, so this is a kind of follow-up for Henry's first question. You said one of the limitations of why you have to go one by one in the superposition is because your tweezer is classical. Is there a possibility of the hardware modification where instead of having one tweezer classically move around, you have some kind of comb of tweezers and that will simultaneously pick and load and unload atoms, and that might save you from some kind of scaling? I don't know if this is possible experimentally.
I think, well, at first, I'm not entirely sure if what you envision is possible theoretically. I think it depends on a couple of these. No, it's just
we're even out of the first level of the concept. Okay.
no. I mean, sorry. What I meant is, I at some point also thought along these lines. I think you need to. Well, at the end of the day, you want the fermion to end up in a single mode, and you also want to be able to do the reverse process. So you need to make sure also that what you do stays a unitary operation. And depending on how exactly one writes it down, I think it's tricky to, do the right thing and keep it unitary and so on. So in principle, I think it might be possible, but I'm not sure right now.
Okay. All right. Thanks.
Are there any questions from the online participants? Okay, well, in that case, Robert, thank you again for the very interesting talk, and thank you for staying up so late. It must be midnight where you are by now. And yeah.
Close to.